Hi, everyone, and welcome to this next installment in my Algebra and Precalculus video series. In this video, we're going to be talking about logarithmic functions. This is the natural next place to go after the previous video, which was exponential functions. And then we're going to talk about a very sort of strong and fundamental connection between exponentials and logarithms. This is something we haven't mentioned yet in any of the previous videos on this playlist, so I'm going to treat this like it's a brand new topic. More like it's new notation, not so much a new topic. So a logarithmic function is a function of the form y equals the log base b of x. So this right-hand side of the equation, this part right here, reading this out loud is the log, log, short for logarithm. Right? We tend to say log, not logarithm, but the log base b of x. Now, the important word here is of, right? The log is what's called a mathematical operator. So let's look at an operator that we've seen before. So the square root. All right, written like this, y equals square root. What does this mean? Well, this means nothing, right? It doesn't make sense, right? Because there's nothing under the square root. When we take the square root, or we apply the square root symbol, we have to take the square root of something. So it would make sense to say y equals the square root of x, or the square root of 9, or the square root of 24, or whatever it is. But an empty square root symbol doesn't mean anything on its own. We need something under it, right? So the square root symbol, that's what's called a mathematical operator. It operates on something. And the thing that it operates on, right, we call this the argument. The argument, right? So we can't have an empty square root symbol. The log, or the logarithm, it operates on something, right? So what we basically have here is y is equal to the log base b. We'll talk about what that base means in a bit, of something. Right? So this part right here is like an empty square root symbol. Right? It needs something to operate on. And that's going to be the other variable x. Right? So we could use parentheses, we don't have to. Either way, it means the same thing. Okay, so we just finished in the previous video talking about, let me go back to that slide. There we go. We just finished talking about exponential functions. Y equals b to the power of x. Where b is a positive number, so b is greater than 0, and also b is not equal to 1. We don't want 1 to the x, because that's actually a constant function, not an exponential function. Up until this point, in every video on this playlist, from the very first video up until now, every definition that I've given has been given explicitly. I've said the definition of this is ... and then you explain what the definition is. I'm going to define the definition of the logarithm in a slightly different way. It's going to be a weird definition. We're going to define it implicitly, so not on its own. We're going to define it in terms of a translation from something else. So we're going to basically start here, start with the exponential function, and then use that to define the logarithmic function. So we're going to define the logarithm in terms of it, like translating from one language to another. So if I were to say, for example, 8 little 2 equal sign 64, right? I'm assuming everyone knows what this means. I mean, well, I'm assuming that if you've watched all of the videos up until this point, you've been coming to class up until this point, then this is something you understand. It means 8 times itself equals 64, or 8 times 8 equals 64. So this should be a pretty straightforward mathematical statement. Well, in another language, another way of writing this would be the log base 8 of 64 is equal to 2. All right, so these two boxes right here, it's saying the exact same thing. It's saying the exact same thing. Just using two different languages. One language is which most likely you are more familiar with, the exponents, and another language that you're probably less familiar with or less comfortable with, the logarithms. Okay, so let me go to the next slide, the definition of the logarithm. Okay, here it is. This is the definition of the logarithm. Y equals the log base b of x. Y equals the log base b of x means the same thing as x equals b to the power of y. Now, the reason that we are talking about exponential functions and then logarithmic functions one after another, and the reason most math books, most pre-calculus or algebra books will do exponential functions and then immediately following exponential functions, we talk about logarithms, is because these two guys are inverses of each other. All right, so I'll use function notation. F of x equals the log base b of x, and g of x is equal to b to the power of x. These guys are inverses of each other. Okay, so our definition, it's an implicit definition. It's not normally how we define something mathematically, but you'll notice there's 3 letters here. We've got an x, a y, and a b. All right, so when you're translating one to the other, it's important that you're putting the right numbers in the right place. And I'm going to do some problems today. And the first problem I'm going to do is going to be translating from log form to exponential form, or exponential form to log form. Now, one pretty common sort of device to remember which numbers go where when you're translating from logarithmic form to exponential form. So what we're going to do very often when we're working with logs is not work with logs. Right? What we're going to do is step 1, translate into exponential form, and then work with the exponential form, because that's something we're probably more comfortable with and have more experience with. So one device that might be helpful, I've seen it before. This is actually how I learned it originally, the scorpion tail. So starting with the base, wrap around the equation, and then back to the argument. So it's basically saying this number, b, that's the base of the logarithm, raised to this power equals this. So green to blue to yellow. Okay, so let's see how this works with some specific examples. Now, this base, the b that I have highlighted in green, it's the same base It's the same base as with a logarithm. So b is a positive number. Right? Same as with our definition of exponential functions. B is a positive number that is not equal to 1. So this applies to exponential functions. This applies to logarithmic functions. Okay, so let's do a problem or two. Before we actually, before we do so, let me talk about, well, let me go back here. So stick with the base, right? There's going to be a couple of numbers, couple of values for B that are more useful, more commonly used, hold more significance than other numbers, right? So we could talk about the log base 2 of x. We could talk about the log base 7 of x. We could talk about the log base 6.14 of x, right? That base could be any positive number other than 1. But there's a couple of values that hold greater significance. So let me talk about those on the next slide. When the base of the logarithm is 10, the log base 10 of x, we call this the common log. We call this the common log. And so you're never going to see this written in a textbook, right? This is what we mean. So let me write this down. This is what we mean but this is what we write. Y is equal to log x. All right, so when you see the letters log for log, short for logarithm, and you have no subscript, no little number after the g, you assume it's a 10. And this is the kind of thing you've seen before, right? The most common version of a thing, sometimes you use shorthand notation. If you're talking about the cube root, you need a little 3. If you're talking about the 4th root, you need a little 4. If you're talking about the 5th root, you need a little 5. But if you're talking about the 2nd root or the square root, you don't write a little 2, right? Generally, you would just see the square root of something, right? And when you see this symbol, the square root symbol with no degree, you know there's a 2 right there. But we drop the 2 because that's the most common version of the square root of the root. That's the most common degree. So same thing with the logarithm. We call this the common log. And it turns out it's so common. Oop, I overshot the button. That there's a button on the calculator for the common log. So this button, log, that means specifically log base 10. Log base 10. And then the other one that has sort of greater importance than any other base, we saw this in the previous video with the natural exponential function, is when the base of the logarithm is the number e. Log base e of x. Well, same thing. This guy is important enough to have its own button on the calculator. There's an ln button. So that's the shorthand notation for natural log. So this is what we mean. Again, same thing with the common log. This is what we mean. We mean log base e of x. But what we write is y equals ln of x. So remember, there's, whether or not we write them, there's parentheses here. That's the log of something, or the natural log of something. So over here, you see on my calculator screen, 2 quick calculations. the log of 41. And the natural log of 3.75. There's nothing important about the number 41 or the number 3.75. This is just a couple of examples. So if you're going to evaluate or calculate a log base 10 or a log base E on the calculator, you've got a button. There's an LOG for log base 10, LN for log base E. Okay, so we're going to be doing some of this on a calculator, some not on a calculator. With the calculator, we're getting a decimal, which means we have to round. And when we're rounding, that means changing. So sometimes that's appropriate, sometimes it's not. Okay. So the first problem I want to talk about, write the equation in its equivalent exponential form. Translate. Translate from one language to another language. So start with the language of logarithms. So I'm looking at this guy right here. Start with the language of logarithms and rewrite it in exponential form. Right? I have the definition down here. Right? This is the definition of the logarithm. So 8 to the power of 2 is equal to 64. I had this up on the screen a little bit earlier. Right, so this statement, 2 equals the log base 8 of 64, and 8 to the second power equals 64. Same thing, right? These two statements are saying the same thing in two different languages. And that's the most important sort of aspect of this topic, that if once that clicks, everything else is going to make more sense. But what we're doing here is we're sort of restating things that we've seen before in a new language. All right, next one. Start with the base. 6 to the power of 6 is equal to m. 6 to the power of 6 is equal to m. We're not going any further. There's nothing to solve for. There's no answer. And we're just rewriting, starting with a statement using log and ending with a statement using exponents. All right, so this problem is going from log form to exponential form, and we could go in the opposite direction as well. So the next question, next problem I want to talk about is same question, rewrite, translate. But let's start with exponential form and then go to log form. All right, notice the letter B is used in both cases. B is the base of the exponent, B is the base of the logarithm. So this exponential expression, 5 to the power of negative 2, so that would be log base 5. Of 1/25 is equal to negative 2. The log is equal always to the exponent. Right? The exponent is on the other side of the equal sign. All right, so when we're looking down here at the definition, we define the logarithm in terms of an exponential expression, something to a power. Right? When we're working with logs, we need exponents. Right? So for the second problem on the right, the square root of 169 is equal to 13. Okay, sure. Square root of 169, that's 13. But to rewrite that using logarithms, it's a bit easier to see when you write your square root, oh, not 19, 169. Rewrite your square root as an exponent. Right, the square root of x is equal to x to the 1/2 power. It's just, again, two ways of saying the same thing. It's like 0.5 and 1/2 decimal fraction, right? So we're applying this to the square root of 169. 169 to the 1/2 power is the same as the square root of 169. So now we've got the log base 169, right? The base of the exponential expression will be the base of the logarithmic expression. Of 13 is equal to the exponent 1/2. Right, so again, these are two statements that say exactly the same thing. Now, one thing that I've covered in an earlier video, maybe 10 or 12, 15 videos back, was that we talked about inverse functions. Two functions that are inverses of each other, or two functions that basically undo or reverse each other. Well, again, the exponential function and the logarithmic function are inverses of each other. So that's important to keep in mind. Okay, next one, evaluate. Evaluate the expression, and we're going to do this without a calculator. What is the log base 2 of 64? Okay, still, it's important to understand what a logarithm is. Okay, later, you're going to have to solve equations and graph functions and simplify and do all kinds of stuff mechanically with logarithms, but none of that has any meaning or any value until you understand what a logarithm is. So this right here, the log base 2 of 64. What is that? What is the log base 2 of 64? Well, it is the exponent. Oh, sorry, not 64, 1 over 64. Let me be precise and correct here. So the log base 2 of 1 over 64, what is it? It is the exponent on the number 2. That gives 1 over 64. All right, so what we're basically saying here is 2 to some power is equal to 1 over 64. 2 to some power equals 1 over 64. And that's what this logarithm is. A logarithm is an exponent. So we're looking for that exponent. All right, so let's see how we could solve for that exponent. Let's say 2 to the power of x is equal to 1 over 64. Okay, well, it's not always possible to solve equations that look like this. The numbers have to be selected in an appropriate way. In this case, the reason we're able to solve this without a calculator, and that's the point here. What allows us to do this without a calculator? Well, if you look at this equation, we've got the number 2 and the number 64. Well, 64 is a power of 2. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64. So 2 to the 6th power is 64. right? And that's important here. We need this. This is what's going to allow us to solve the problem. Right? So we got 2 to the power of x is equal to 1 over, instead of 64, I'm going to write 2 to the power of 6. Right? What I want to do is match up both sides of this equation so they're exponential expressions with the same base. 2 to the power of something on the left, 2 to the power of something on the right. Well, on the right, we've got 1 over 2 to the 6th, but we have a rule of exponents. Let's say a negative sign in the exponent means reciprocal. So 1 over 2 to the positive 6 is the same as 2 to the negative 6. So 1 over 64, we could rewrite as 2 to the negative 6th power. And so if 2 to the x is equal to 2 to the negative 6, we have the same base on both sides. Well, then the exponents have to be the same. If 2 to this equals 2 to that, now this equals that. So x has to equal negative 6. Okay, let's do another one of these where we start with the logarithmic equation, rewrite it in exponential form, and then try to match up the base of the exponential expression on both sides. The log base 8 of 2, what is this equal to? Well, it's equal to something, right? So let's say it's equal to x. We could have, this is a little bit different than the way I've written it. This is a little bit different than the way I wrote up the last one, but we're doing the same thing. We're taking a logarithmic expression and rewriting it in exponential form. 8 to the power of x is equal to 2. 8 to the power of x is equal to 2. The same thing with the last problem. 8 is a power of 2. 2 times 2 is 4, times 2 is 8. So 2 to the 3rd power is equal to 8. So we could swap out the 8 on the left-hand side with a 2 to the power of 3. There's still a power of x. Like, we haven't touched that yet. Okay, and one of our rules of exponents says that if you have an exponent raised to another exponent, you multiply the exponents. So the left-hand side would be 2 to the power of 3x. And on the right, any number raised to the first power is equal to itself. So we've matched up the base. 2 to a power equals 2 to a power. So those two exponents must be equal. So if 2 to the 3x is equal to 2 to the first, then 3x must equal 1. We can divide both sides by 3, and that will give us x is equal to 1/3. X is equal to 1/3. So sometimes we're able to evaluate without a calculator. Sometimes we're not. We'll talk about when we're not and how to do that a little bit later. I think I'll do that in my next video. But what's important so far, everything we're doing relates back to this definition. Right? When you start with an equation or an expression in logarithmic form, you could always rewrite it as an exponential expression. Okay, now going back to what I said earlier, that the exponential function and the logarithmic function of the same base are inverses of each other. So what we want to do here is graph the function f of x equals 5 to the x. And g of x is equal to the log base 5 of x. In the same rectangular coordinate system, or basically two graphs on the same plane. Now, the way we're going to do this, is going back to our previous discussion on inverses. So this function and this function are inverses of each other. They're inverses of each other. Now, one thing that we talked about with inverses is that if the ordered pair x comma y is coming from one function, we'll say x comma y is a point on the graph of f of x, so it's an ordered pair from f of x, then the point y comma x is on the graph of g of x. So when you go from a function to its inverse, you're sort of swapping out the x's with the y's. The x's of one function are the y values of the other. The y values of one function are the x values of the other. So what we saw was that when you have two functions that are inverses of each other, their graphs will be mirror images of each other over the line y is equal to x. Okay, so let's graph the first one. F of x equals 5 to the x. That guy is going to have a horizontal asymptote at y equals 0. I'm not going to talk too much about how to graph 5 to the x. That was my previous video, the one right before this one. So if you're a little unsure about graphing exponential functions, maybe pause and go back to the video right before this one. But I'm going to look something like this. All right, so this is the graph of f of x is equal to 5 to the x, passes through the point 0, 1. That's the y-intercept. So when we take that green graph, the exponential function, and reflect it over the line y equals x, well, the point 0, 1 becomes the point 1, 0. And we get this sort of mirror image of the graph. The asymptote reflects as well. So that green horizontal asymptote becomes this blue vertical asymptote. Okay, so the green one is the exponential function 5 to the x, and the blue one is the logarithmic function g of x equals the log base 5 of x. They are mirror images of each other reflected over the line y equals x. Okay, so one thing we saw with the exponential functions is that the domain is all real numbers, negative infinity to infinity, and the range of that function is everything above the horizontal asymptote, all those y values above 0. So 0 to infinity. And then from what we know about inverse functions, when you then, sorry about that. When you go from the function to its inverse, well, what happens? So we're going to talk about g of x is equal to the log base 5 of x. The x's of one are the y values of the other. The y values of one are the x values of the other. The x values are the domain. The y values are the range. So that means the domain of the green function is going to be the range of the blue function. And the range of the green function is going to be the domain of the blue one. Domain of a function is the range of the inverse, and the range of a function is the domain of the inverse. This is something we've seen in previous discussions, previous videos, previous functions. We're just taking that discussion and applying it now to the exponential functions, and now this new type of function, the logarithmic function. You cannot take the log of a negative number. You cannot take the log of a negative number. Because you cannot take a positive number, raise it to an exponent, and get a negative number back. It's just not possible. Right? The base of the logarithm, in this case, log base 5, you cannot take the number 5 and raise it to a power and get a negative number. 5 to a positive would be positive. 5 to a negative would be positive. 5 to the power of 0 would be positive. Everything's positive. Okay, we don't need a graph. I mean, if we're going to talk about domain, it's helpful if we have the graph, but it's not necessary. Not necessary. So the next problem, 2 problems on the same slide. Find the domain of the function, and we're not going to actually graph here. Right, back here on this problem, we had the graph. You could see on that blue graph, yeah, the domain, all the x values above 0. But now, let's look at this guy. What is the domain of the function m of x equals 3 times the log base 5 of x plus 4? Well, the rule is you cannot take the log of a negative number, right? So the function on the left, m of x, is 3 times the log base 5 of x plus 4. So you're applying the log to the x plus 4. You're taking the log of x plus 4. So if you're taking the log of something, that something has to be positive. Actually, we could state this in a bit stronger, in a stronger way. You cannot take the log of a negative number, or let me stick with red, or 0. So no negative numbers, no zeros as the argument of a log. So for this first one, you're taking the log of x plus 4, so x plus 4 has to be positive. Right? You're taking the log of x plus 4. It doesn't matter that's base 5. It could be base 7, base 2, base 1.8. Doesn't any base. Natural log, common log. Any log of x plus 4 means x plus 4 has to be positive. And then the same thing on the right with n of x. If you're taking the log of 3 minus x, then 3 minus x has to be a positive number. It doesn't mean x has to be positive. It just means that the thing inside the parentheses, that has to be positive. So if we solve for x, minus 4 from both sides, we get x must be bigger than negative 4. So in interval notation, that would be, nope, not negative infinity. That would be negative 4 up to infinity. And that would be the domain. The one on the right, we could add x to both sides. So we get 3 is greater than x. 3 is greater than x, or x is less than 3. So x is any number below 3. So negative infinity up to, but not including 3. So there's a lot of things that we've talked about previously with other types of functions: evaluating, simplifying, factoring, graphing, domains, ranges, things like this. These are all things that we could now rediscuss or bring back up in the context of exponential and logarithmic functions. Okay, so one more problem. Let's solve an equation. Let's solve a couple of equations. So our goal here is solve for x. Solve for x. Well, what does this mean? What does this mean? It means when the base is 5 and the exponent is 2. Remember, the exponent is always on the other side of the equal sign. Right? When the base is 5 and the exponent is 2, you get x minus 3. All right, so I've rewritten this statement, this equation. Log base 5 of x minus 3 equals 2. I've rewritten this in exponential form. 5 to the second power equals x minus 3. And this is a much more straightforward problem to solve. 5 to the second power, that's 5 times 5, which is 25, is equal to x minus 3. Solve for x, so we could add 3. Add 3 to both sides. So those 3's cancel. We've got x is equal to 28. You may be wondering if every single statement involving a logarithm means the same thing as another statement in exponential form, then why do we need both? Why do we need both? Well, we'll talk about this a little bit later when we get into more application problems, but sort of a short answer is it allows us to measure things using different scales. Right? You're probably used to measuring things in a certain way. Whether you're measuring inches or pounds or dollars or years or whatever unit you're using. Well, if you look at 2 pounds, and then you look at 3 pounds, that's an increase from 2 to 3, plus 1 pound, right? And then from 3 pounds to 4 pounds, that's an increase of 1 pound, right? Nothing crazy going on here. And then from 4 pounds to 5 pounds, same thing. So it's a linear scale. The difference between consecutive numbers is equal. So if we look at this on a number line, well, 2 to 3 versus 3 to 4 versus 4 to 5, they're all equally spaced on the number line, 5 to 6, 6 to 7, so on. These numbers are all equally spaced. A log scale, using logarithms to describe measurement, is not linear like this. The difference between the 1 and the 2 is not the same as 2 and 3, and that's not the same as 3 to 4. Like one example, let's see, what's an example that you may have heard of? Let's say the Richter scale. Has anyone heard of the Richter scale, the scale for measuring the intensity of an earthquake? Oh, I heard on the news the other day, California had a magnitude 3.2 earthquake. Right, that 3.2 measured on the Richter scale that's saying, okay, 3.2 means it's bigger than 3 and smaller than 4. It's somewhere between 3 and 4. But what does that mean? Well, the intensity of an earthquake, let's say there is no earthquake. Intensity is 0. A really small earthquake, probably wouldn't even call it an earthquake, more like a tremor. That would be a 1. But then a 2 on the Richter scale, an earthquake of magnitude 2 does not look like that, right? 2 is actually way over here. And then 3, well, 3 wouldn't even fit on the screen. 3 is way over here off the screen by another probably, 12, 15 inches. Right? So the distance between consecutive numbers is multiplied by 10. Right? So from 0 to 1, the distance is 1. But from 1 to 2, let's give this an arrow, the distance is 10 units between 1 and 2. And then from a magnitude 2 to a magnitude 3 earthquake, well, the distance between those two numbers on this scale is 100. Or actually, that would be, yeah, well, 100 units, 1 unit. Everything is, if we call this 1 unit, 1 unit, then the distance between the 2 and the 3 is 100 units. And the distance between the 3 and the 4 is then 1,000 units, and so on. So it's this non-linear scale of measurement. It's a little bit outside the scope of this class to discuss, the nuts and bolts of what this means. But there are some benefits, especially when things get really, really, really small or really, really big, to work with logarithms rather than a linear scale. Okay, now that was a little bit of a tangent. Let's come back to one more problem, solving an exponential equation, which is a result of this logarithmic equation. So we want to start with this. convert this to exponential form, and then solve. So we've got 2 to the power of -5 is equal to x. 2 to the power of -5 is equal to x. Oh, we're already done. I mean, we've solved for x. X is 2 to the -5. Conventionally, though, we don't want to leave negative exponents as our final answer. So let's simplify 2 to the -5 power. Remember, a negative sign and an exponent means reciprocal. So that's 1 over 2 to the power of 5. And 2 to the 5th power, that's 2 times 2 times 2 times 2 times 2. 5 2s will give us 32. So solve for x, 1 over 32. Okay, before we could solve any more complicated problems, we're going to need a few more tools in our toolbox. So in this next video, I'm going to talk about some properties and some rules of logarithms that will allow us to attack somewhat more complicated problems. So that's it for this video. Just an introduction to what is a logarithm. And then from here, the next one, we'll get into some rules and some properties. And then from there, we'll get into solving some more equations. All right, that's it for now. I hope this was helpful.